Hey guys, today we're going to discuss the next variable within thermodynamics, and that's going to be entropy. Now, entropy is a measure of disorder of a system. So something with high entropy is largely disorganized, and something with low entropy is very organized. So what we're going to discuss today is both the premise behind entropy and then the application of entropy into our topics here in chemistry. So let's start by discussing the generalities of entropy. The first thing to be aware of is that in chemistry we're going to use the letter S to represent entropy. Therefore, delta S represents the change in entropy, just like delta H represented the change in enthalpy. Entropy is a measure of disorder or randomness. So the greater the value of S, the more positive the value of S, the greater the entropy of the system would be. So again, a higher magnitude of value there would be an increased entropy compared to a lower value. Now all of this relates back to the second law of thermodynamics. This is not something that you need to necessarily be completely aware of for this course, but just so you're cognizant of it, the second law of thermodynamics essentially says that entropy of the universe is always increasing. And in order to decrease any form of entropy, we have to actually apply energy. So one way that I like to kind of envision entropy is with a bedroom. Now, I don't know about your bedrooms, but my bedroom tends to get a little bit messy if I don't do anything to actively clean it up. So as time goes on, my bedroom continues to become a little bit messier and a little bit messier and a little bit messier. And that's not something that I'm actively doing, right? It's almost passive in the sense that I'm not actively trying to make a mess of my room. It just happens to become messy. In order to then clean my room, I have to engage. I have to add energy. I have to put in time and energy myself to be able to clean up my room and make it neat again, right? You can think of this like the binders that you use in this course, right? Over time, the binder becomes a little bit more cluttered. Right? Why? Well, you start accumulating more things, more stuff, higher entropy. So let's talk about the things that lead to increased entropy, and then we're going to go ahead and apply this in a chemical sense. Now, based off of the second law of thermodynamics, you can think of entropy as kind of always wanting to increase. In other words, it's thermodynamically favorable for entropy to increase as opposed to decrease. So, whenever we look at the course of a chemical reaction, if delta S is positive, right, so there's an overall increase in entropy from reactants to products, that suggests that we have a thermodynamically favorable process. If delta S is negative, which means that the entropy decreases, in other words, the system becomes more organized over the course of the reaction, that is a thermodynamically unfavorable process. The things that we can look at as having an impact on the entropy of a system are kind of in decreasing order: the phase, the number of molecules, the size of the molecules, and finally the organization of the molecules, or how the molecules themselves are built. All of these things can change the entropy of a system. And so we're going to look at each of these kind of in order of what has the greatest effect to what has the least effect. So let's start with the phase. Now, if we think about phase, a solid is going to be very organized. By its nature, molecules are kind of stuck in position. They're not really moving around. They're vibrating, but they're essentially organized in a crystalline structure or in a solid structure. That is going to be very low entropy. You compare this to a liquid, where your entropy is going to be increased because now all of a sudden you can have your molecules in more configurations. We call these microstates. So microstates would represent all the different ways that a molecule can exist. It can be over here, over here, over here, and all the different ways you can organize any molecule represents an increase in the number of microstates, therefore an increase in entropy. Now, in a liquid, we have increased entropy, but in a gas, now all of a sudden we have massively increased entropy. Anytime a gas is present, the entropy is extremely high compared to when there's a liquid or a solid present. So if we look at this example reaction, on the reactant side we have a solid, and on the product side we have gases. That suggests that we have a massive increase in entropy of this system due to the phase change that occurred. The second thing we can look to determine whether there's an increase or decrease in entropy is going to be the number of molecules. Now, I'm going to prioritize the number of molecules of gas in this case. If the phase doesn't change, then we simply look at the pure number of molecules. But in this case, if we look at this example, this would be the combustion of butane, C4H10. What we see is on the right side, we have more molecules of gas or more moles of gas than we do on the left side. This represents a net increase in entropy because we have more molecules of gas. So here, with just the gas, it's now looking at, instead of a phase change, it's now looking at the number of molecules of gas. If everything stayed liquid, then the more molecules of liquid we had, or the more moles of liquid we'd have, would be shown as the increase there as well. So again, first thing we look to, phase change. Second thing we look to, the number of moles of the highest entropy phase within the reaction. The third thing we can look to when it comes to determining changes in entropy over the course of a reaction is going to be the size of molecules involved. Now, in this case, it's a relatively small impact, so it's nothing like it was with phase change or even number of molecules, but a larger molecule has greater entropy. And the reason for that is because of the fact that that molecule would show greater numbers of microstates. So a molecule is not just a fixed thing. Molecules can rotate around bonds and vibrate across bonds and move, and all of these differences in their pattern and orientation can create more microstates. So a larger, longer molecule has greater microstates than a smaller or more compressed molecule. So if I were to compare methane, CH4, to butane, C4H10, the butane would actually have higher entropy even within the same phase. Let's say they were both gas. They would both be the same phase, but the butane, because it has more microstates as a larger molecule, would have higher entropy. Now, one of the most minor components of determining entropy, and one that we're not going to really get into very much, is also the bonding within molecules. Later in this year, we're going to discuss the relative bond structures within atoms and molecules. But in this case, just be aware that the more bonds that exist, right, so double bond or triple bond, which I know are words that you haven't necessarily heard yet, those are going to represent lower entropy than single bonds. Okay? So we're going to, again, talk about those bonding structures later in the year, but just to put it in your head now, single bonds are going to be of higher entropy than double or triple bonds. So just to wrap up how we're going to determine if entropy is going to change during a reaction. First thing we look at is the phase. Is a gas created or is a gas used? If there's a gas on one side but not the other, then the side with the gas is inherently going to have higher entropy. The second thing we can look at is going to be the number of molecules. Specifically, if there are gases on both sides, the number of molecules of gas is going to dictate which side has higher entropy. The side with more molecules of gas or more moles of gas is the higher entropy side. Third thing we look to is the size of the molecules. Again, this is relatively minor. So if we have everything else equal, phase and number of molecules, then the size of the atoms is going to determine change in entropy, where a larger molecule has higher entropy than a smaller molecule. And finally, the actual chemical construction of the molecules themselves. Single bonds would be higher entropy than double or triple bonds. So let's do a practice problem where I'm looking to find the delta S of this reaction. In this case, the decomposition of beryllium hydroxide. Now, this process, I'm given the entropies of all three of my species involved. So I've got the entropy of solid beryllium hydroxide, solid beryllium oxide, and gaseous water in this case. So I've got all three. Now, as would be expected, both of the solids have a much lower entropy than my gaseous water, and the less large, as it were, solid, the beryllium oxide, has a lower entropy than my larger solid, which is the beryllium hydroxide. So again, this falls right in line with what we would expect, given the number of microstates each would show. Now, to solve for my change in entropy, I do it the same way I did with my change in enthalpy. It's the delta S is equal to the sum of the S of my products minus the sum of S of my reactants. So what I'm going to do is first write this given that format. So delta S, sum of products, sum of reactants. Now, identifying my products, beryllium oxide and water, each of these is in a coefficient of 1, which means I take both of these values, the 13.77 and the 188.83, I multiply both by 1, and I'm going to add them together. Okay, so 13.77 times 1, the coefficient on my beryllium oxide, 188.3 times 1, which is the coefficient of my water. I then take those values and I subtract the value of my beryllium hydroxide, again multiplying that by 1 because of its coefficient. If I solved all the way through this, what I would end up with is a change in entropy, a delta S, of 152.3 joules per mole Kelvin. Now be careful. Notice in all of my entropy values, these are all in joules per mole Kelvin. This is different than what we saw with our enthalpy of reactions, where it was always represented in kilojoules. So just be careful with the units here. Again, we're in joules per mole Kelvin. Now, as would be expected, we go from a side with one solid to a side with a solid and a gas. We change phase. We've added a gas. That suggests that we should have seen a positive change in our entropy, which we do. Positive 152.3 joules per mole Kelvin. So that wraps up today's video. Again, you're going to be expected to calculate the delta S of a reaction just like you were expected to calculate the delta H. In the next video, we're going to apply both change in enthalpy and change in entropy to a new variable that we call free energy. I'd like to thank Afam Okiki and Matt Hiller for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.